and we crossed out all the multiples of 2. Now we'll move on to the next unmarked cell. What does the unmarked cell signify? It basically signifies the numbers which are a prime number. So now when we move on to the this number 3, we'll cross out all the multiples of 3. So 6 is already crossed out. We'd cross out 9, then we cross out 12, which is already crossed out. Then 15, then 18 is crossed out. 21, then 27, then 33, then 39, then 45, and 51, and after that we'd cross out 57. So now we cross out all the multiples of 3. Now let's move on to 5. So one thing which you have to understand is that we have to start crossing out only from I square, because from 5 we have to start crossing out only from 5 square, which is 25, then 35, then 55. Why we're doing that is, let's say we cross out some other number 15. So 15 is already formed, it's crossed out by the numbers preceding 5. In this case, it's 3 into 5. So it's already considered by all the numbers before 5. So you have to start crossing out only from 5 square. So that's what you do. You would cross out 15, 25, 35, 45, 55. All these are already crossed out. So now we've crossed out the multiples of 5. Now we'll check 7. And again, we'll check from 7 square itself, because all the other numbers which are crossed out are already accounted by the preceding numbers. So 7, the first number which will cross out is 49. So then after that, 56 is already crossed out. So we just need to cross out 49. And now the next prime number is 11. And 11 square is 121. So it's not in this range. So there's nothing we need to cross out. You can even verify it, 22 is crossed out, 33 is crossed out, 44. So now what's remaining? These are all the prime numbers, which is less than 60, less than or equal to 60. And so this is what the Sieve algorithm has done. It's able to generate a list of all the prime numbers less than 60. And the time complexity of this thing is, it is, once again. Okay. Yeah, the time complexity of the Sieve algorithm is O of n into log of n. So now this time complexity, the derivation is quite lengthy and it involves lots of math. So it's out of scope for this lecture, but you can check it out. You can just Google it and you'll find out how we get this time complexity. So now let's try implementing this Sieve algorithm by writing some lines of code. So we'll make a function called Sieve, and we'll take an input the number int n, and the first thing which we'll do is we have to now iterate through all the elements, and we have to start crossing out the composite numbers. So we'll first run a for loop for int. Okay, before doing all this, first we have to generate an array which will be used to store the numbers. So we'll give it a global definition. So we'll write an array. Array is, okay, sorry for that. Int is prime n. We'll actually give it once again. We'll put this inside here, Control X, and we'll the size of it will be n+1, because your the indexes would be marked from 0 till n. So that's why we are making the size n+1. And once you declare this array, you have int n. And so now we'll run a for loop for the elements of the array. The first thing you have to do is you have to initialize all the elements of the array as 1, because initially you're assuming that all the elements are uncrossed. So that's why we'll first do that for int I equal to 2, I less than equal to n, I plus, and is time of I equal to 1. So this will make all the elements of its prime as 1. And we are not considering I equal to 0 and I equal to 1, because that's not required in this case. And now after we do that, now we'll run a for loop, which will be used to implement the Sieve. So for int I equal to 2, I less than equal to I into I is less than equal to n, and I plus plus. So okay, one more thing which I forgot to tell you all is that over here we just need to consider like I into I. Like we need not check for all the prime numbers. Like we stopped at 11 here, so we didn't have to check for 13, 17 because 11 square exceeded 60. So that's what we're doing in the code, that we are writing I into I is less than equal to n. It'll only iterate till that much. And within this code, what you do is you would check whether your element is unmarked or marked. Initially, all elements are unmarked. So like what we'll check is if is prime of I, if it's like, so inside this now, if it is unmarked, then you would start another for loop, which would be used to cross out all its multiples. So for int j equal to, we need, like as I said, we have to start j from I into I square, because all the other elements which is less than I square would already be crossed out by the elements which are less than j. So j equal to I into I, and j should go like until j should be less than equal to n, and j plus equal to I, because now we're checking the multiples of I. So we have to increment j by I every time. That would give you the multiples. And you have to then make is prime of I equal to 0. That means whenever you encounter a multiple, you have to cross it out. So that's what we're doing by assigning it the value of 0. And after doing this, you can actually like then exit from this loop. So once this these two loops completely like run, so you like this would basically iterate for all the prime numbers, and over here you're basically checking like you're crossing out all the multiples of the prime numbers. So finally what you would have achieved is you would have like ended up crossing all the multiples of prime numbers. So you would only be left with the prime numbers. So now all you have to do here is you just have to see out once you finish both these loops, and you just need to see out, like not see out, like first you have to check whether the number is prime or not. So if it's prime of I, first we'll actually make a for loop for int I equal to 2, I less than equal to n, I plus plus. If it's prime of I, like if I is a prime number, so then you would just see out I, and so it would this program would basically output all the prime numbers which is less than n, and this return one is not required actually. So okay, let me just check if it's right, and okay, it seems fine. And here what we do is we just call the function, like we'll have to input n and we have to just is prime of n. So this okay, wait, Sieve, I actually messed up a little bit. Actually, this array is like I've written is prime of I. It's actually it's an array, so I have to write is prime with a square bracket, and the function name is Sieve. So I have to call Sieve, and I just hope this is correct, and let's just rebuild it. So I don't think there's any error here. Let's try inputting a number 10. Okay, I think I've done some mistake somewhere. Let me just have a look. It's outputting almost all the numbers. So we call a number, we put it in this function Sieve. So it takes an integer, and it has an array here is prime, and the size of it is n plus 1. And we run a for loop from I equal to 2 to n, I plus plus is prime of I equal to 1 initially, and for n I equal to I'm not able to find out what I did wrong here. Let me just have another look at it and see if anyone can identify my mistake. You can just like point it out.
I just raised his hand.
Okay, yeah. Yeah, you can unmute yourself. Is it possible? One second. I think the hand went down, so I don't know. Yeah, Raj, you can unmute. Hello.
I think he's having mic issues again. One error that I saw pointed out in the chat was in the second for loop, the J
Yeah.
for loop, you have to write is prime of J to be 0. Line
Oh yeah,
18.
sorry. Yeah. I did a mistake. Thanks. So now let me just have a look. Okay, not this, sorry. This is I. This would be J. Okay, now let's just try building it and running it. Okay, thanks, Aditya. It's working now. So I hope you all understood this implementation. So what we have done is in the main function, we have declared n and we're inputting it. So this was a problem statement that we have to input n and we have to generate all the prime numbers less than n. And then we're calling this function Sieve. And within the function, what we're doing is first we are declaring an array of size n+1. So this would have all the numbers as the index from 0 to n. And once you have the array, then you're running a for loop and initializing all the elements of the array with 1. And after initializing it with 1, then you're running another for loop. This for loop is for crossing out all the multiples of the prime numbers. So you started from 2 and it goes till like as long as I into I is less than or equal to n. So when I is like, so this for loop will go, like it'll run, this is the condition for the for loop. And within the for loop, you are checking whether a number is not crossed out. So that means is prime would return 1, is prime of I. So if it's not crossed out, then that means it's a prime number and you're crossing out all the multiples of that prime number. And the only points which might be a bit confusing is the limits, like I into I is less than equal to n. And even this part, like j is equal to I into I. This is because, as we saw earlier also, that suppose like n is equal to 5. No, let's say n is equal to 6. So after I is equal to 3, like the square of I would then become 9. So after that, we need not consider like I, because whatever has to be considered like would already be done by the numbers lower than I. So what I'm saying is that in this case also here, that like if we consider 13 or 11, so any multiples of 11 or 13 are already like taken care of by the numbers preceding these numbers, the prime numbers preceding them, like 5 or 2. So that's why we're only running it till like as long as I into I is less than equal to n. And even here we start j is equal to I into I, because even like I'll just show you here. So like suppose if we consider 3, so 6 would already be crossed out because it's a multiple of a number less than 3, which is 2 and 3. So you need to start it from only like I into I. Like so 9, you started from 9 because 9 was uncrossed at that time. So yeah, that's the code, guys. And if anybody has any doubt, you can ask me. Okay, I guess nobody has any doubt so far. So I'll move on to the next topic. So this is a simple sieve, like this would be quite useful in many problems. And now there's another concept called segmented sieve. And this is a this is basically a space optimized version of a normal sieve. And this is very helpful when you have to find like the number of like the prime numbers that lie between a given range. And usually it's really helpful like if you're like if the range is a very high value, like suppose you have to find the prime numbers lying between 10 raised to 9 and 10 raised to 10 or some like really high values. So the segmented sieve is very useful. So what the concept of segmented sieve is, like I'll just show you guys in Zideboard. So let me just go to the next slide here. So you have to like I'll go through the steps. So first you input two numbers L and H. Then you generate all the prime numbers from 0 to floor of square root H. Then you have to create an array of size H minus L plus 1 that represents the number between H and L, and mark the multiples of the prime numbers obtained in step 1 that are present in the array. The remaining unmarked numbers would be prime. So I'll now I'll give you an example to show how this works. Let me just clear everything. So let's say numbers which are given are, let's say a range is 7 to 13 or 14. Let's say 7 to 14 is your range of values. So you have to find all the prime numbers that lie between 7 and 14. And 7 and 14 is inclusive to the like range. So what we'll do is the first step, let's look. So we have to generate all prime numbers from 0 to floor of square root h. So square root h would be square root of 14. So square root of 14 would be like 3 point something. So you have to just generate it till the floor of it. So the only two primes would be 2 and 3, which so you have generated your prime numbers. Now what you have to do is you have to create an array of size h minus l plus 1 that represents the numbers between h and l. So so h minus l plus 1 basically gives all the numbers like 7, 8, 9, 10, 11, 12, 13, 14. So that would be h minus l plus 1, which would be 8 in this case. So you would have an array of 8 elements, 1, 2, 3, 4, 5, 6, 7, 8. So these arrays are indexed in the normal way, like 0, 1, 2, 3, 4, 5, 6, and 7. But the values corresponding to these, like 0 would actually correspond to 7, 1 would correspond to 8, and so on. 7 would correspond to like 14 in this case. And now what you'll do in this case is also like initially you'll assume all of them to be true. Like true in the sense the values are 1. That means you're assuming them to be a prime number. So t, 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 all would be t. And as you like proceed, so what you do is you cross out all the multiples of 2 in this series. So like this is actually 7, 8, 9, 10, 11, 12, 13, and 14. So you'd cross out all the multiples of 2, and so 8 would be crossed out. So this would become false. Then 10 would be crossed out, which would become false. Then 12 would be crossed out, which would become false. And 14 would be crossed out. After that, now you'd cross out all the multiples of 3. So over here, you would have like 9, which would be crossed out. This would become false. And you would have 12, which is already crossed out. So these are the only numbers which will be crossed out. So the remaining numbers, which is like 7, then you have 11, then you have 13. All of these are prime numbers. So again, now here, what we're doing is, so we have generated an array here, like of prime numbers 2 and 3. So this is basically floor of square root of h, the size of this array. So h is this number, l is this number. So you've generated one array of size floor of square root of h, and the size of this is h minus l plus 1. So now suppose you're given a number which is very high, like if h is 10 raised to 9 and like l is, you can say like 10 raised to 8, 5 into 10 raised to 8 or something like that. So in that case, so the like if you were implementing it using a normal sieve and you would generate all prime numbers until 10 raised to 9, and then you would put like you would output all the prime numbers by putting the limits. So in that case, you're actually making a like your space complexity would be very high. You would be making an array of like h size. So in this case, you are reducing the space complexity by making an array of only like the size of the array square root of root h in this array, and the size of this array is h minus l plus 1. So usually h minus l, they'd give it really small, like 10 raised to 9 minus 10 raised to 8. Like it'll be some like 9 into 10 raised to 8 or something. So like the size would be really small. It would just be like okay, this is also a really high value. They would give it like some 9.99 or something like that. So you'll have some number like 99887 or 54, something like this, and you'd be given like 10000000. So 1 2 3 4 5 6, 1 2 3 4 5 6. You'd have another 0 here and 1. So if you're given two ranges like this, so h minus l would not be a really high value. It would be like something, it might be like 1000 or 2000. So even this array is quite small, and even this array is quite small here, 2 and 3. So you have actually reduced the space by a huge margin, because initially you had to generate like 10 raised to 9. The number of elements of the array would be 10 raised to 9. Here you have reduced it. So that's why this is a very space optimized algorithm. So now the question is, how would we implement this in code? So again, now we'll write some code to show how we implement this. So for this case, I'll do it all within the main function itself. So let me just say, like, I'm using long because you might like get really high values in the question. So that's why long n suppose. So sorry, long L and H. So these are your two limits which you inputting, and then you would input them C in L, H, and after that you would so the first thing is you have to generate a array which represents all the prime numbers which is less than or equal to square root of H. So for this we'll use a sieve to implement this. So we'd use a traditional sieve that so first we'll write an array int of prime, and the size of this would be square root of H. So and we'd only like measure till the floor of it. So floor of square root of floor of square root of H, because if square root of H is not an integer, so then you have to take the floor of it, and you're adding 1 because it's also inclusive of the floor of square root of H. Otherwise the index would be 0, 1, 2, 3, 4 till floor of square root of H minus 1. So you add 1 just to include this upper bound also. And usually the compiler throws an error, so I'll just I'll typecast this whole thing into an integer because it says that you can't have a float inside an array. So that's what I've done here. So I've declared an array prime whose size is floor of square root of H plus 1. So once I've declared this, now I'll initialize. Yeah.
I have a doubt. What is floor of square root of H? I don't understand that part.
Yeah, I'll just explain here. So even here, what we saw, like we took the numbers as 7 and 14. So it is only required to generate all the numbers till square root of 14, because let's say you use 5 to check. So now 5 would, so now if you check over here, you have like 7 to 14. So now 10 would come between 7 and 14, but 10 is already crossed out by 2 into 5. So what we have to do is we just have to generate like all the prime numbers till square root of H. It's not required to generate prime numbers beyond that. We can do it, but it's just occupying extra space because any prime number beyond square root of root H is already accounted for by a prime number which is already like encountered. Like in this case, like 2 into 7 was giving 14. So we need not check for 7 because it's already counted by using 2. So that's why the size of this array would only be square root of like square root of H. So actually I did a mistake here. It's just square root of H. So so did you understand?
Well, size of the array means square root of H, it will be like root of 14, it's less than 4. Then the size will be 3.
No, actually, over here you even have other elements like 2, 3, 4, 5, 6. I mean, square root of 14 would be 3. So you would have like 0, 1, 2. But none of the other elements are considered because only these elements are prime. So we have to generate all prime numbers less than square root of H.
Okay.
So like, yeah, so here what I'm doing is I've just made an array called prime. So this array, like so far it doesn't include only the prime numbers. It also includes the composite numbers. But we'll use the Sieve algorithm to only generate the prime numbers in this array. So that's what we're going to do now. Like we'll use the same Sieve algorithm. So we'll initialize all the values as 1. So for int I equal to 2, I less than equal to square root of H. So here we'll initialize the value as 1 for each I. So once we do that, now every element in the in this array prime would be initialized with 1, but we have to just find out the prime elements. So we'll run a sieve for this thing. So we'll now run another for loop. So now we're running a usual like sieve algorithm. So we start j from I into I, and j less than equal to like the last element, which is square root of H, j plus plus. And so we'll just cross out like j plus equal to I, and we'll just cross out all the elements. So prime of j would become 0. So here we're crossing out all the composite elements. We are taking all the multiples of the prime and crossing it out. So I guess so this should perform the task, and we'd also enclose this. So what this did is, like, first it assigned the value of 1 to all the elements in this array prime, and after that what this sieve does here, it will just make all the prime numbers, it will assign the value of 1 to it, and all the composite numbers will have a value of 0. So now once you're done with this, then you have to the next step is you have to create an array of size h minus l plus 1 that represents the numbers between h and l. So now you'd create an array in, let's just create an ll, and let's name it is prime, and we'll create the sizes h minus l plus 1. And once you have created this, now you'll again run a for loop, and you have to assign all the values as true as we did over here. So we'll assign all the values as true initially, and later we'll cross out the ones which are composite. So we'll do that. Now we have also generated the is prime array. Is prime array represents like this one, h minus l plus 1. It represents this array, and your prime array represents this array. So now once you've done that, now we have to just cross out all the multiples of 2 from this array. So now we'll do that using another loop. So now let me tell you what's the next step to do. So now we basically obtained this array which represents all the prime numbers less than or equal to square root of h. And we've also generated another array who's initially we assigned all the values as true. And now we have to cross out all the multiples of these prime numbers which are located in this array. So what we'll do is we'll iterate through all the elements of the prime array. And so now first we'll select the element 2. So now we have to check out all the multiples of 2 which occur in this array. So first thing which we'll do is this is L here, 7 is L, and 14 is H. So we only have to start from 8 because 8 is the first multiple of 2. So how would we obtain 8? We'll basically take L upon I into I. So now I is 2, we're iterating through this array. So first when you take the element 2, it would L by I, which is 7 by 2, which would output 3. And when you multiply it by 2, you would get 6. So your index would start from 6, this is assumed to be 6. But now 6 does not lie in this range. So what you'll do is, if L does not divide I, if it leaves a remainder, you would just add I to this. So this was at 6 initially, it would now become 8. So you would check this element, which is 8. And then you would start crossing out the multiples. But if it already if it would divide it, suppose let's take suppose how do I put it in? If you take if this was the only array which you're considering, 9 to 14, if L is equal to 9 and H is 14. So when you take 3 and when you find out the starting position, so this would be the starting position. You just divide L by I into I. So this would return 3 because 9 by 3 is 3, and when you multiply it by 3, you would get 9. So it would start from this position itself. So we need not we need not add I in this case because it's already starting from the 9th index. So what we have to do is we have to check out whether L by I is an integer or not. If L by I is an integer, if L divides I, if I divides L, then we need not add plus I. But if I does not divide L, so to bring L by I into I to this range, we would add I to it. So I'll just show you what we are doing here. So we'll declare an integer int a is equal to L by I into I. And so now first we'll check if L by I is, if L mod I is not equal to 0, that means it leaves a remainder. So then you have to just write a is equal to a plus I. And if so now this is the only thing which you have to consider. Otherwise, the starting index is this value. But like if I does not divide L, then you have to increment a by I to bring it into the range. And then now you'll start cancelling out all the multiples. So for int j equal to a, you'd start it from a because a is the starting index, and you'll start cancelling. So j is less than L, less than or equal to L, j plus plus. And now is prime of j, you'd make it equal to 0. Sorry for this. So here you're like basically if you're assigning it the value of 0 means you're considering it's a composite number, so you're crossing it out. So that's what this for loop does, and this would finish the implementation of this for loop. So far what have we achieved? Like what we've done is first we found like we declared an array prime, and then we initialized its value as 1, and after that we found out all the prime numbers in that array. And so after doing all this, we found out the prime numbers in the array. Then we are writing another, like we are declaring another array is prime, whose size is h minus L plus 1. And we are also assuming the value of each element is 1. And after that, within this here, you're basically crossing out all the multiples located in is prime. And so if like the element in your prime array is prime, so then you would cross it out, like the elements of is prime. And here I've done a small mistake. It will be j minus L because we are starting the indexing from like 0. So whatever like your value is, like if like j is starting from somewhere near L, so you have to subtract it from L, because suppose j was L, so then it's the index position is 0. If j was L plus 1, the index position is 1. That's why you have to cross out is prime of j minus L. And so when j reaches L, you would cross out j reaches h. So when j reaches h, you would cross out h minus L. So this is what this loop does. And after we finish this, let me see if there's any mistake here. And okay, here also it will be an array. So once you finish crossing out everything, then you just have to like output all your. See, let me see where this leads. Okay, this is an extra. So after you finish crossing out the elements, now you'll run a for loop for int I equal to L, I less than equal to h, I plus plus. And here you would just, if the element is a prime number, then you would output it. And so yeah, that's what you're going to do here. And now let's just see, there would be a couple of errors, I'm sure. Yeah, wait, okay, sorry, here it will be a. Let's just try 8 to 15. Again, it seems that I've done some error. Let me have a look at it. LLLH, you're inputting LNH, then you're declaring a prime array like of size floor of square root of h plus 1, and okay, let me just see what's wrong in this. And int I equal to I is less than equal to square root of h I plus plus. Prime of I, you're initializing it as 1, and I into I is less than equal to square root of h I plus plus. If prime of I, then prime of j is equal to 0. And LL is prime h minus L plus 1 for int I is equal to 0. I is less than h minus L plus 1, I plus plus is prime of I is equal to 1. S prime of I is equal to 1.
In line 39,
Yeah,
shouldn't you be incrementing in jumps of I?
in line 39. Oh yeah, sorry. That's another mistake. Yeah, so we have to like cross out the multiples. So that's why you have to increment it in jumps of I. So now let me just run and check. One second.
You give J plus I. J plus
Okay.
equal to I.
Again, I think there's some mistake. Let me rebuild it once. There seems to be some mistake here. Once again. S prime J minus L is equal to 0. I plus S prime is C out number and I is less than equal to square root of H. S prime of I is equal to 1. Okay. Okay, I think I did a mistake here. It will be like we'll run I from 0 till H minus L plus 1. And if S prime of I is true, then we'll see out I plus L. So now let's just have a look at it. Okay, so now it seems to be working. What I did a mistake here is that your array is indexed from 0 to like H minus L plus H minus L. So now if you would have to like output it, so you check whether like the particular index, if it's like true or false. So if it is true, that means the number is prime. So then you have to see out I plus L, because the index is like the index and the true range differ from like by L. So that's why you'd have to output this. And let's just check for some other value, 7 and 25. 7, 11, 13, 17. Okay, so now it seems to be working. So if you guys have any doubt in the code, you can ask. Hi, yes, Vineet, you can ask. Yeah, Narasimhan, you can ask.
Can you just show your code once?
Yeah, I'll just show it. Like,
Aditya, can you do one thing? Can you select all the full code?
yeah.
Control A,
And the,
and then
yeah.
can you format it? It might be easier for them to see.
Okay.
Control A, right click.
Yeah. And like
and you
format
get format
use.
user style. Yeah,
Okay.
it will kind of do a bit of indentation, so it might look better if people
Yeah,
are
it looks better.
where which loop is.
Yeah. So if anybody didn't understand, once again, I'll explain the code. So like what I'm doing is initially I'm just declaring L and H, which is the limits between which you want to find the prime numbers. And then I input L and H. And after that, the first thing I do is first I generate an array. The name of the array is prime. What this array does is it just has all the elements, like it has all the numbers that lie between floor of square root of H plus 1. And why floor of square root of H plus 1? Because we basically want to check all the prime numbers, and we are going to use those prime numbers to cancel out all the elements that are located between L and H. So that's what we're doing over here. And so now we have to find all the prime numbers within this range, like floor of square root of H plus 1. We have to find all the prime numbers within that. and we're going to use those prime numbers to cancel out all the composite numbers in the other array, which we declare here. LL is prime H minus L plus 1. So this is the array denoting all the numbers of the given range. So now what we're doing is we are using the Sieve algorithm to find out all the primes until like square root of H. So that's what we're doing here, as I showed before, like the same Sieve algorithm. And once you generate all the primes, you're using those primes to cross out all the composite numbers within the range of L and H. So what we're doing is we are like declaring an array LL is prime H minus L plus 1, and the size is H minus L plus 1 because these are all the numbers within the range like L to H. So you're first assigning the value of 1 to each element, because initially assuming like all the elements are like uncrossed. So that's why we are assigning the value 1. And after that, we are running a for loop for I is equal to 2. And as long as like the loop will run as long as I is less than equal to square root of H. And so what we're doing here is we are just crossing out all the elements of the array is prime. So you'll only be left with the prime elements after crossing them all out. So if your element in the array prime is prime, that means this would have a value of 1. So you would now find out like A over here, this would just represent the starting index of from where you have to start crossing out. So like you have an is prime array. So is prime might start from say like 1000, and like the upper limit might be 1200. So we need not check for all the numbers less than 1000. We only need to start canceling from 1000. So that's what we're doing here. So this represents the starting index from where you have to start canceling the multiples of the prime numbers. So we first write L by I into I, and if L by I is not an integer, that means I does not divide L, it leaves a remainder. So then you have to increment it by I, because otherwise A would lie like A would be less than L, but you need to make A more than L, because A should lie between L and H. So that's why you would add I to A. And after you do that, then you just start canceling out. You like go in multiples of I, and you cancel out all the like composite numbers. And after you cancel them out, even here, like we are writing J minus L, because J would be some number lying between L and H. And the array which you have declared, the index is starting from 0. So that's why you have to write J minus L. So suppose L is 100 and H is 120. So if the element which is like which you're considering is like 120, so you have to write 120 minus 120, because the array which is storing them is indexed from 0. So if it's 126 or something, so then it would be 126 minus 120. So the sixth index position would be assigned the value of 0 if it is prime, if it is not prime. So then after we generate this, now we'll generate like all the prime numbers within the range. So then you just output it. You run like from I equal to 0 till I is equal to H minus L. And then you have to, if the number is prime, so then you have to output I plus L. Why I plus L? Because again, like the index is starting from 0, but we are checking only from H, like we're only checking for the range of L to H. So that's why we'll output I plus L. So now if anyone has any doubt, you can ask, or then I'll proceed to some problems.
Aditya, we are just lacking a bit of time.
Yeah, so I guess you can then like Aditya, so you can take over. We'll see in the end if there's any time left, so then we can do some problems on this topic.
Yeah, sure. So
Yeah.
if you have any doubts till whatever has been taught, you can ask it out. If we can move on to the next session of the next part of the session. You can raise your hand or you can write it in chat. Okay, Aditya, I think there are no more queries, so we'll move on to the other Aditya now.
Yeah, I'll stop presenting. Thank you, guys.
Thank you, Aditya.
Yeah.
Okay, so I'll take over.
Yeah, sure.
Okay, I'll start presenting my screen. And yep, am I visible and is my screen visible?
Yeah, we can see you and your screen.
Okay, cool. So yeah, so in this part of the lecture, we'll be looking at modular combinatorics and exponentiation. So this is all just big words that I took from Google, so don't worry about it. So I'll be starting from scratch about Modulo, and at the end of the next 30 or 40 minutes, I hope we will learn a lot along the way. So it would be nice if everyone is with your keyboard, so that I'll be asking questions in the middle. There were many questions, so I was not able to put in a form of a form or something. So you can just enter your answer in the chat, irrespective of whether someone else has entered or not. And for some things, you might even need a pen and paper, so it's good to have that as well. So topics to be covered, I'll start with modulo and its properties. So how many of you here are aware of what modulo is? Like A percentage B. How many of you are aware? You can raise your hand so that I'll see. Okay, only one person knows? Okay, I think this is a good way to take attendance. So how many know modulo? For them will get attendance. Okay, I think hands are increasing. So in maths, the modulo operation is used to return the remainder of a division. So basically, if you have two positive numbers A and B, A modulo B is the remainder that you get when you divide A by B. So these are all pretty basic. 14 is equal to 5 into 2 plus 4. So the remainder is 4. So 14 modulo 5 is 4. Similarly, 23 modulo 7 is 2. And 9 modulo 3 is 0. So till this, it should be fine. And if you have any doubt at any point in time, raise your hands. And for modulo, you can put down your hands. So that's fine. And when one of them becomes negative, this definition kind of breaks down, and what happens when you give 14 minus 14 percentage 5 is dependent on what language you're coding in. So in C++, at least with code forces and code blocks, if you give minus 5 percentage 3, it outputs minus 2. So it'll take the quotient of this division to be minus 1, and the remainder of this division will be minus 2. So whenever you have negative numbers, try to refrain from doing division, because integer division won't happen. When you do minus 5 by 3, you're not going to get minus 2 as the output. You'll get minus 1 as the output. So be careful when you're dealing with negative numbers. So for the sake of fun, you can just try out and see what different combinations give minus 5 percentage 3 or minus 7 percentage minus 3, like here. But for the rest of the session, so on this point in time, we'll only be dealing with A percentage B, where A is non-negative and B is positive. I hope that clears up what modulo is. So now let's start with some properties of modulo. So A plus B whole percentage n is A percentage n plus B percentage n whole percentage n, naturally. So any doubts here? I don't see any hands raised. I think the hands already raised the previous queries. Okay, so I see no doubts with this property. Let's move on to the next one. So A minus B mod n. So suppose, assuming A greater than B, A minus B mod n will be A mod n minus B mod n plus n mod n. This plus n is present so that this whole quantity remains positive. Because for negative numbers, we'll come up with issues like how we saw implementation issues in C++. So in the case of negative numbers, what we'll be doing is, when you have A minus B, we'll just add a plus n. So that's one thing. And then the third thing is AB mod n. So when you have product of two numbers, AB mod n will be A mod n times B mod n whole mod n. So how exactly would you try to prove this? So for that, what we can do is we can take A to be n cube plus r and B to be ns plus t. So this is the regular dividend equal to divisor into quotient plus remainder thing. And then when you multiply A and B, the only term without an n term will be r into t. So AB mod n is equal to RT mod n. So product of RT could be more than it. So it's better to take a mod after we find RT as well. So this third property is very important. So if you guys have a doubt in the third property, do raise your hand now itself. So, okay, I don't see any hands raised. So move on to the next one. And from this, so if I just replace B with some doubt, yeah.
No, I actually had a doubt in the previous slide. Like in that negative example, what exactly is happening is you just remove the negative sign and then you insert it in after the answer is calculated.
Yes. So it will do division like 5 by 3. Quotient will be 1. So to the quotient, we'll put a minus sign. Quotient will come as minus 1. For the remainder, will be 2. So it will put a minus 2.
Oh, okay. Okay.
You can try out other combinations as well. 5 percentage minus 3. I think the results will be different in both cases. So you can check out all those when you see. But because of this, try to avoid having negative arguments here when you use percentage as well as division.
Okay. Thank you.
So the fourth property is, you can just extend third property, replace B with A. So you'll get a square mod n is a mod n the whole square mod n. A cube mod n will be a mod n the whole cube mod n. So on. A power b percentage n will be the remainder whole power b mod n. So this is also just derived from here. Now we did addition, subtraction, multiplication. Is there anything for division? What about, suppose I have 6 and 3 and I want to find 6 by 3 mod 2. And you can say, okay, 6 by 3 mod 2 means you can just divide and then just directly find. No, but there's a reason why we want to have this given a and b, I want to find a by b mod n without doing the division. So let's say for now we can't do division, and just given a and b, I want to find the value somehow. So there's no direct formula for a by b mod n. Like there are conditional formulae, there's a conditional property, but for all n, at least to my knowledge, there's no direct formula, right? There's no directly a by b mod n equal to a mod n by b mod n, nothing like that. That's wrong. So there's a conditional property, and the conditional property is very useful. So we're gonna go and try to see what we can do to a by b mod n. Before we can go there, there's a prerequisite theorem that we need to understand. So some of you might have seen in 11th or 10th, Fermat's little theorem. So if p is a prime number, then for any positive integer a power p is congruent to a mod p. So now what does this, I've introduced a new symbol here, something like congruent to. So when I say a congruent to b mod p, that means both a and b give the same remainder when I divide with p. So if I have a congruent to b mod p, then a percentage p equal to b percentage p. Essentially, with respect to modulo p, both are identical. Both numbers on the either side of the congruent sign, they give the same remainder when divided by p, right? So this is the theorem. I'm not going to give you a proof. If you want, if you're interested, you can go into it. But as of now, we are more interested in the application of this than the proof. Now, if a is not divisible by p, from this I can say that a power p minus a is divisible by p, because both give the same remainder, which means if I subtract them, the remainders will cancel and the difference will be purely divisible by p. So in Fermat's little theorem, we know that a power p minus a is divisible by p. And now LHS is divisible by a, because you can take a common and that will be a times a power p minus 1 minus 1, which means RHS should also be divisible by a. Now p is a prime, and we said a is not divisible by p. So a cannot be captured in p, which means a should be captured in q. So q is a multiple of a, so let's say q equal to ka. K is some positive integer again. So a power p minus a is now equal to kap. Now I cancel a on all sides, so you get a power p minus 1 equal to kp. So this thing you can write as a power p minus 1 is congruent to 1 mod p. So this is also Fermat's little theorem only. It's just that if it's not divisible, you can write it in this neater form as well. The nice thing is you have a 1 here. So a power p minus 1 when divided by p gives a remainder of 1. And this theorem is very crucial in our future discussions. So do you have any doubt in the statement of the theorem and what we have brought it to? Any doubts? Okay, I don't see any doubts. Cool, no issues. Now, we have generally heard of additive inverse, right? So we say, okay, there's a doubt. Yeah.
Sorry, I just have a doubt. Can A be 1?
A is 1 means 1 congruent to 1 mod p. That's all.
Okay.
So yeah, actually this theorem is actually applicable for all whole numbers, 1 and 0. So but then when you come here, you can't do 0. So this is applicable for any positive integer. Yeah, okay, I guess that doubt's clear. Now I'll move on to modular multiplicative inverse. So this was there in the title itself, right? So I had put some modular exponentiation and combinatorics and all. So we are slowly going into there. So in modular language, additive inverse of a is minus a, because when you add minus a to a, the remainder that you get is 0. It's like additive inverse of a in general. A plus something should give you 0. That's something is minus a. Similarly, here a plus something should give you remainder 0 mod n. So we just take minus a itself. You could say n minus a can come and all, but we'll just deal with minus a and all. Similarly, you generally like additive inverse, you also have something called multiplicative inverse. So multiplicative inverse of a is 1 by a, we say, because product of them is 1. So in terms of modular language, so when I say modular language, when we are dealing with modulo, is there a multiplicative inverse of a with respect to modulo? And the answer is yes. there is, but not for all numbers, under some conditions on a and n. So we do have a multiplicative inverse. So what the multiplicative inverse will be is, it will be a number x such that ax is congruent to 1 mod n. Instead of the product being 1, the remainder that it gives with when divided by n should be 1. So the modular multiplicative inverse of a number a with respect to modulo n. So this multiplicative inverse is defined for a pair of numbers. For a number a with respect to divisor n. So it depends on both. It's not like it just depends on a. It depends on both a and n. So it is an integer x such that ax is congruent to 1 mod n. So any doubts on what the definition of multiplicative inverse of modular multiplicative inverse is? I'll just be calling it mod inverse from now. It's abusive notation, but it's more convenient. Any doubts? Okay, no doubts. So everyone is clear with what modular multiplicative inverse is? Mod inverse is? Okay, so mod inverse of a number a with respect to n is an integer x such that ax is congruent to 1 mod n. Now that we've seen the definition, for what kind of pairs a comma n is it defined? Because I said there are some terms and conditions. It's not defined for all a and n. It is defined if and only if a and n are coprime. If and only if a and n are coprime, I will have such an x. If they are not coprime, I will not have such an x at all. And hence, there will be no mod inverse.
Can you show a few examples for the modulo thing? Like
this one? Multiplicative inverse?
Yeah, what x will be for a few a and n?
Okay. So yeah, I'll do that. So now let's now that we've seen that it has to be coprime, let's take two numbers that are coprime only, 5 and 7. So let's say this was a was 5 and n was 7. So what do you guys mod inverse of 5 with respect to 7 is? You can put in the chat. So how are we supposed to check me? You can just brute force. So I don't see any answers so far. 5 and 7. What is the answer? Even I'm not sure. Okay. 5. Okay, so one answer that I got is 5. So if x equal to 5, then ax should be congruent to 1 mod n, right? By definition. So what is ax? Ax will be 25. 25 divided by 7, what is the remainder? The remainder is going to be 4. It's not 1. Okay, now I got another answer, 3. So if we change this to 3, so 5 3s are 15, and 15 by 7 gives a remainder of 1. Yes, we have mod inverse. So let's take another example as well then. They need not be prime numbers, they just need to be coprime numbers. So maybe with that regard, let's take 4 and 9. Okay, I'll take n equal to 4 and a equal to 9. I am also not sure of the answer, so I'll also need some time to think. What works for 9 and 4? Okay, for which one you're saying? For this one 10? Yeah, 10 also works. So if you do 15, 5 into 10, 50% 7 is also 1. So from this we have found one interesting thing. The modulo inverse of a number need not be unique, right? Because we also had 10, we also had 3. Now what is unique for 10 and 3? 10 is basically 3 plus 7. So and 7. So basically 5 into 3 worked. To 5 into 3, what did we do? We added 5 into 7. And 5 into 7 is not going to give any remainder when divided by 7. So whatever this gives as a remainder, only that will be there. So 1 and 0. Which means the modulo inverse of 5 with respect to 7 can be of the form, we said 3, right? So can be of the form 3 plus 7n. Because 5 into 3 will give you a remainder of 1, but 5 into 7n will give you a remainder of 0. So modulo inverse of a number is not unique. That is one property. And for 9 and 4, I think one was told and one is the answer. One works. Yeah. So for 9 and 4, 1 will work, 5 will work, 9 will work. As Nasiman said, it will be an arithmetic progression. Yes. But what we want generally is we will try to go for the mod inverse value which lies in 1 to n. So we will try to go for the first value that we want. That helps us computationally. There are reasons for that. But from 1 to n, there will always be a value. And if you add n to this, you can just add kn to this whatever value. Let's say alpha is the value that worked out. Alpha plus kn will also serve as a suitable modular inverse. But generally, we will only deal with the value in 1 to n. So it's like, this is like the principal domains from which we'll take mod inverse. So is that clear on a few examples for mod inverse? Yeah, 5 you can do, but then we will only consider from 1 to n generally. You can still say that it's not wrong in saying that 5 into 9, when you divide by 4, the remainder is 1. It is true, the remainder is 1. But we will focus on 1 to n, right? So any doubts in the chat? I think some nice replies came. So do you want me to do some more examples or something? Okay, maybe we'll do the third example, no issues. So let's take 14. Let's go with bigger numbers now. 14 and 23. Can we find? No, it might take too much time. Wait, I think okay, 5 and 14. 5 and 14 should be doable. Okay, 5 and 14 is probably too easy, but okay, take 14 and 5. So A is 14 and B is 5. Yeah. So if A is 14 and okay, not B, N is 5. What is X such that AX percentage N should be 1? Yes, I got one reply in the answer. Do you guys think that's correct? Even if someone has answered before, even if you're going to put the same number, it's absolutely fine. Put the same number. So that way I'll know that people are listening to what I'm saying, right? That will be motivating for me as well. So yeah, I think 3 4s have come. And yeah, 4 works. 14 to 4 is 56. 56 percentage 5 is 1. So we have been, so far we've just found manually. And I'm always giving you the guarantee that between 1 to n, you can always find the mod inverse for A, right? Mod inverse of A will always lie in 1 to n, the least value at least. And suppose if you try for 6 and 9, you are not going to get any mod inverse. So intuitively also you can see a reason, because AX is going to be divisible by 3, N is also going to be divisible by 3, so the remainder should also be divisible by 3, right? So the remainder should also be divisible by the GCD of these two numbers, which means the remainder can't be 1 because the GCD is not 1. So we'll continue to the presentation. Any doubts so far on finding modular inverse manually at least? Manually you just check from 1 to n and whichever works. So okay, in the chat I see no doubts. So now I will go into another theorem. You don't need to know this theorem. It's just if you're interested in why this condition is there, you can see it. And you would have also seen this theorem before in one of the SPC problems. So if you have A and B to be integers with the greatest common divisor D, then there exist integers x and y such that ax plus by is d. More generally, for whatever x and y you pick, ax plus by will be multiples of d. So this has a nice proof as well. I am not sure what to Bezout use, but I have a nice proof that will be used for modulo inverse as well, but I'll not do it for now. I'll give you some time to think and maybe you can do it in a later session. So now, how is this Bezout's identity useful? If GCD of two numbers is 1, or let's say GCD is not 1. If GCD is not 1, any numbers of the form ax plus by or even ax minus by are going to be divisible by g because they're all multiples of g. G is the GCD. And for mod inverse to exist, we need ax minus 1 to be ny because ax should be congruent to 1 mod n. So ax minus 1 should be divisible by n, which means ax minus 1 equal to ny will translate to ax minus ny is 1. But then we said ax minus ny should be divisible by g, and 1 is not divisible by g. And hence, if the GCD of two numbers is not 1, if two numbers are not coprime, you cannot find a modulo inverse for it. Right? Now, if two numbers are coprime, by the theorem itself, there exist numbers such that ax minus ny is 1. And because of that, you have ax congruent to 1 mod n, hence mod inverse exists. Still, this has not shown that mod inverse will exist within 1 to n, and there will be exactly one unique number in 1 to n. That I'm going to leave as an exercise. And the Bezout's identity proof also, this you can prove it with intuition. You don't need to know any high level concept or something. So you can try it out and check or even Google it. Now, is mod inverse unique? Yeah, we just saw it from Nassim's example. So if x works, x plus n works, but we will only When I say mod inverse of A comma n, I mean what values x can take, but we will only focus for the values between 1 to n. So again, this was an exercise for you guys. So now, we have learned about mod inverse. Mod inverse is some number such that Ax congruent to 1 mod n. So what exactly is the use of mod inverse? So what our initial goal was, before seeing what Fermat's theorem was, our initial goal was, if I have two numbers A and B, can I find A by B mod n in terms of A and B, or do some computation on them, but I don't want to divide them. Assume that I am incapable of dividing them. So the prerequisite now that we have found out is B and n must be coprime. So that's one prerequisite. So mod inverse, you can kind of link that I'm going to do something to this 1 by B. So because of that, B and n should be coprime numbers. We'll see why. Now let us say A by B is C. Now as B and n are coprime, there exists an integer x such that Bx congruent to 1 mod n. This is basically the modulo inverse. And let's assume somehow some genie has given us the value of mod inverse of B with respect to n. Let us say this is known to us, right? Now we have B and n to be coprime, and we have the modulo inverse of B with respect to n. So x is there. What I will now do is I will multiply C to both these numbers. So if we know x, we know Bx. Multiply C on both sides of the modulo congruence. Why can you do this? You can do this because if A percentage n equal to B percentage n, then AC percentage n equal to BC percentage n. You can get this from property 3. Property 3 was AB mod n equal to A mod n times B mod n whole mod n. So AC mod n will be A mod n times C mod n whole mod n. This side will be B mod n times C mod n whole mod n. A mod n and B mod n are equal, hence these two values are also equal. So because of that, I can multiply C on both sides and I can say CBX will give the same remainder as C when divided by n. Now my whole goal was to find what will be the remainder when C is divided by n. So that will be the same as the remainder when CBX is divided by n. And CBX is equal to A, because so CB is equal to A. So CBX will be AX. So my goal was finding A by B mod n, which is basically C mod n. And then I did some math. I cooked up a new number called modulo inverse such that Bx congruent to 1 mod n. I multiplied C on both sides. It became CBX and C. CB then I called A. And then I'm saying AX is congruent to C mod n. So the remainder when A by B is divided by n is the same as the remainder when A into X is divided by n. So it's like this 1 by B got replaced with some number called mod inverse. So it's like 1 by B is equivalent to 1 by B percentage n. This is purely abusive notation. When I say 1 by B percentage n, there is nothing called as fraction percentage n, but you can, if you want to imagine something as this as A percentage n into 1 by B percentage n, if you want to apply property 3 to this, you can. And 1 by B percentage n will be this term mod inverse of B command. It will be this magic number that a genie has given us by computing, right? So A by B percentage n, now I have a method without doing this division. If I know this mod inverse value for B and n, I can just multiply it with A and take the remainder with n. So far, do you guys have any doubts? If I have gone fast, I'll go back and even tell that again. No issues. Any doubts? Yeah, it's abusive notation. Because if in a math exam you go and write 1 by B percentage n, the professor is just going to tear your paper. So it's just wrong. There's nothing called 1 by B percentage n. So you should use the term mod inverse or something, right? So any doubts so far? Even if you have to go 3 or 4 slides back, do tell me. I'll go back. You can raise your hand or something, right? No doubts? No one understood anything? Or was I that good? Oh, okay, fine. I'm gonna assume I was that good. So I'll move on. Now we said that for in this case we assume that, let us assume we know x, some genie gave us x. Now let us try to become that genie and find mod inverse of B comma P where P is prime. So what did we do from the start? From the start we learned about what modulo was, and we saw some basic properties: addition, subtraction, multiplication. And then we wondered, what can I do if division comes? Can I, without dividing the numbers, just by using what A and B are, can I try to find A by B mod n? And then we said, okay, there's a prerequisite theorem. It's called Fermat's little theorem, and then I gave you the theorem. After the theorem, what did we do? After the theorem, we explored something called modular multiplicative inverse. We went to mod inverse. We did not do anything with the theorem and mod inverse. We went to mod inverse where AX equal to congruent to 1 mod n, and we saw some examples for it. And after seeing using the concept of mod inverse, I was able to find A by B mod n. Now, where does Fermat's theorem come into all this puzzle? I started A by B mod n. For A by B mod n, I defined something called mod inverse, and using mod inverse, I was able to find A by B mod n. But then now I don't know how to find mod inverse. How do you find mod inverse without having to check for each number by hand? So all the examples we did so far, we are checking by hand. Suppose I give numbers like 2733 and 3434. I don't even know if they're co-prime. Can you find mod inverse without actually writing all of them? You can brute force them, but then if I give you numbers of size 10 power 9, so if I give you 1e9 plus 7 and I give you some 998254353 something, if I give you two big numbers like that, you can't keep checking from 1 to n and check if alpha into n is divisible, right? You can't go and check every multiple of a. So what we do is we use Fermat's theorem, and Fermat's theorem, this method of finding mod inverse is applicable only if P is prime. The concept of mod inverse is applicable if B and P are co-prime. P need not be prime for finding mod inverse. But then for applying Fermat's theorem, you need P to be prime. So we are studying a subset case of finding mod inverse where P is prime. Now that we have fixed P is prime and we know Fermat's theorem, Fermat's theorem said that if B is not divisible by prime P, let us assume not divisible. If it's divisible, it's going to be trivially 0, right? So if B is not divisible by prime P, then B power P minus 1 is congruent to 1 mod P. This was Fermat's theorem. And then what is mod inverse? Mod inverse is now defined. Mod inverse of B comma, okay, this should be mod inverse of B comma P is a number x such that Bx congruent to 1 mod P. So B power P minus 1 gives the same remainder when divided by P. Bx also gives the same remainder when divided by P. So now, can I say one solution to x is B power P minus 2? Because I'm just equating these two numbers. So one solution to x is B power P minus 2. Because this works and this works, I'll just equate both, that's all. And now that I've equated both, now that we said if x works as a mod inverse, x plus n will also work as a mod inverse. Similarly, if x plus n works as mod inverse, then x will also work as mod inverse. So from that we can say B power P minus 2 percentage P also works. So any doubt from this to this? So what we did is I had to find mod inverse. For mod inverse, what I did, I used Fermat's theorem where we had this nice 1 coming, and then I said, okay, Bx should also give me 1, B power P minus 1 should also give me 1. So I will equate both, and I found one value for x. I found a solution, one possible solution for mod inverse of B comma P, where P is prime. This is a strict condition. Always remember P is prime. From now, whenever we talk about mod inverse, we are going to restrict to P is prime. We are not going to talk about P non-prime case, right? So we equated both, and then we said one solution to x is B power P minus 2, and I wanted a solution 1 to n, so I will take modulo with respect to P. That's gonna give me a number in 1 to P. So this also works. So we found one solution for mod inverse of B comma P, which is this thing. Whether this is the only solution or not, I haven't proved yet, and I have left it as an exercise to you guys. Any doubts so far? If you didn't understand anything till this point also, you can raise your hand. Okay, if everyone understood, please raise your hands. No one raising hands. Okay, if you understood what happened so far, raise your hand. Because this is the math behind what we're going to do. After this, I'm going to give you a bunch of functions, and that's all. You'll just use the functions in your code. But if you know the math behind it, you will know where to use and when to use. Okay, so I see 17, 18 people, so that many people are listening, fine. Hence, mod inverse of B comma P is B power P minus 2 percentage P, one of the solutions. So I am summarizing all that I've done so far. If P is prime, and if I want to find A by B mod P, what I can do? I can do A into mod inverse of B comma n percentage P. We saw that in the previous slide. And in this slide, we found that it was going to be A into this value. And here we have A B mod P. So I'll write it as A mod P into B mod P whole mod P. So A by B percentage P got converted to product. And once we got a product, we can nicely manipulate products like this. So this is what mod inverse is used for. So I'll go to the next slide now. Now let's forget about mod inverse. So far what you learned, keep it in mind. And now let's start with the game, right? Let us hypothetically say a computer can deal with numbers up to 10 power 10 power 10. Also, in this computer, assume addition, subtraction, multiplication, division. Each of them takes 1 second to do. Now, in how many seconds can you find? How many seconds can you write you have to write a code, and how much time will that code take to find the value of 3 power 10 power 9? And your error can be up to plus minus 1000%. So your answer by correct answer can be in the range of 0.1 to 10. Any of that is accepted. Please put your answers in the chat. You have a computer that can deal with numbers up to this much. So currently C++ and all can only deal up to 10 power 19. But I'm giving you a magic computer that can deal up to these numbers. And in these computers, if you want to do addition, it takes 1 second. Subtraction of two numbers, 1 second. Multiplication, division, all of them take 1 second. In how many seconds can you find this big number? So you can even put out the worst case scenario as well. So like the naive approach to computation as well. That's absolutely fine. I just want you guys to put out some number so that you have an idea of how to find a power b, right? If you don't know how to find a power b, then I'm not sure what exactly can be done. So yeah, all the place in chat. 1e9. Yes, that's a possible answer. You can just keep multiplying 3 continuously. So 10 power 9 seconds. So that's another answer. Okay, so 10 power 9 works. Is there something less than 10 power 9 that can work? Okay, yeah, 10 power 9 works. So if you think answer is 10 power 9, do put there, right? Do put 10 power 9. 1e9 plus 9, okay. 1e9 plus 9, that also works. I'm not sure why. Okay, yeah, yeah, I gave an error of 1000%. So yeah, you can even giving 1e9 is absolutely fine. Okay, any other answers? More efficiency is, you can't spend 10 power 9 seconds living, right? 9 to calculate 29. Okay, yeah. So you can't I don't think your lifespan is for 10 power 9 seconds, right? I don't think you can live to that much. I'm not sure. So anything better? Anything better? Something that you can do better? Okay, cool. Now I am giving you that I can do this operation in minutes. Right? I've written 1 minute here, but I can do it within minutes. I have 1000% allowed, right? I can do it within a minute, but how can I do it in such a short time? So that's a question that everyone will have in their mind. Log 1e, yes, log something of the order of log 1e9. So of this order around, so it's like you will have a 1000% error around 1e9, log 10 power 9. So that is the time that I will take. Now, how will I do this? How am I so fast at multiplication? So what I'm going to do, I'll maybe open Zideboard for this. So yeah. So what I'm going to do, I'm going to compute 3 power 2 power I. Basically, I'm going to start computing 3 power 1, 3 power 2, 3 power 4, 3 power 8, 3 power 16, and so on. I'm going to keep computing until I find 3 power something which is more than 1e9, 1e9 plus. So I'll put something there, right? Okay, I'm out of it. So I'll find 3 power 1, 3 power 2, 3 power 4, 3 power 8, 3 power 16, and I'll keep finding 3 power 2 power I for I from 1 to j, where j is the least number such that the power exceeds. So basically, until this number exceeds 1e9, I will keep doing. So how many numbers am I creating? 2 power j should be just less greater than 1e9. So j will be greater than log 1e9. Excuse the bad handwriting, it's the mouse. Base 2. So j will be this much. So I think this should be around 30. I'm not sure if it's 31, 32. Assume it's around 30, right? So first I will find 3 power 1. Then I multiply once to find 3 power 2. So these numbers I can find within 30 seconds, right? I can find these numbers because 3 power 1. Then I will multiply 3 to it and then I'll store it as 3 power 2 instead of finding 3 power 2 from scratch. And then I'll square this to find 3 power 4 instead of multiplying from scratch. So from this number to this number, I can go in one multiplication. So I can find all these numbers in one step, right? So I found this in 30 seconds, right? Now, Everyone clear with what I'm doing first? I'm finding these numbers first, right? Once I have found it, what I'm doing is, so I think the power was 10 power 9. So this is the binary representation. Okay, it's very huge. I copied it from somewhere. So let's assume binary representation of 10 power 9 was this for now, right? Assume 10 power 9's binary representation is this. Now, what I will do, so basically I have 3 power something. So I will go to the ith bit. So this is the first bit. So 1. Okay, maybe I'll call it the 0th bit. This is 0, array indexing 0, 1, 2, 3, so on. So this is the 0th bit. The 0th bit is 0. So I'll now initialize a variable result to 1. Result equal to 1. Right? Now, the 0th bit is 0, so I'll not do anything. Now, the first bit is 1. I will multiply this number, a of 1. Let's say this array was a. I will multiply a of 1 to result. So now result will become 3 square. Now, I'll go to the next bit. Next bit, in the second bit, I have a 0, so I won't do anything. I'll go to next bit. Now I'm the third bit. Third bit, I have a 1. I will multiply a of this bit. So this is the third bit, so I'll multiply a of 3 into 3 power 8. Now I'll go to next bit, 0, next bit 0, I'll go to next bit. So this is the 0, 1, 2, 3, 4, 5, 6th bit. So what should the 6th bit contain? Should contain 3 power 64, right? 3 power 2 power 6. Basically these hold 3 power 2 power 8. So now this is a 1, so I'll multiply 3 power 64. And next one is also 1, so I'll multiply 3 power 128. So in each step I am doing one multiplication, right? So rest equal to rest into 3 square, rest equal to rest into 3 power 8, rest equal to rest into 3 power 64, rest equal to rest into 3 power 128. So this is what I have done. So in this case I have done 4 products. So the maximum number will be when all of them are 1, so you'll keep multiplying. So that is going to take you 30 seconds. And the number that I have got will be 3 power sigma, so 3 power 2 plus 8 plus 64 plus 128, right? 3 power 2 plus 8. This is basically, what is this number? This number is basically this. This should have been 10 power 9, but here whatever number it was, it will be the number b that I had written in binary representation. So I have computed 3 power whatever it is within 1 minute. So 1 in 10 seconds is 31.7 years. So okay, you might live that much time, but if I ask you to find for 3 numbers and you have only one computer, you can't find. But then now I have found the product in 1 minute. First this computation, and then index by index I will check if the bit is 1 or 0, and depending on that multiply. What is the time complexity of this? The number of numbers I'll store here is log b, right? And the number of bits in b will also be log b. So I'm taking order of log b steps. So do you have any doubts in how I multiplied? I might have gone a bit fast. So if you have doubts, raise your hand. I'll check if anyone has raised your hand. If you want me to explain how I multiplied again, I can go there. So I will store the bit representation of b, and I will store this thing 3 power 2 power I for each I. And if the ith bit is 1, I will multiply 3 power 2 power I to this. So any doubts so far on what I have done, on the process I have done? You don't need to be able to know how to code this right now. It doesn't matter. If you understand the process, it's fine. So have you understood the process? I'm not seeing any raised hands. Okay, if you have understood the process, please raise your hand. This is very crucial to see what's going to happen in the future. So I initialize result to 1. I travel through the bits of 1e9. If the ith bit is 1, I'll multiply 3 power 2 pi to the result. Else I don't multiply. Now the final result will have 3 power summation of 2 pi says that ith bit of 1e9 is 1. Exponent will be 1e9 itself. Number of multiplications I did is first for finding the 3 power 2 pi once, and then for iterating through once, 2 into this thing which is less than 60. Okay, so I see 6 hands raised. I guess that's fine. You can lower your hands. So I did it in 1 minute. Now, what would be the code for this fast multiplier? So if I want to find a power b, what I'm doing is I am storing result equal to 1 and a power equal to a. So initially I am setting I to 0. So a power 2 power 0 a. Now you guys, I think you would remember how you would convert a decimal number to its binary representation. You'll do while b is not 0. If the b percentage 2 is 1, that bit is 1. So the ith bit, the 0th bit is 1. And then you'll cut off that bit. How do you cut off that bit? So for example, I'll maybe go through that once as well. So b was 1 1 0 0 1 0 1 0. So first I will find if the remainder of b with 2 is 1 or not. So I'm starting here. So this bit is 0. So this is not 1. So maybe I'll put a 0 here. I don't know the number right now, but assume this is the bit representation. And then when I divide by 2, what happens is, it's like this bit just goes off and all these bits remain. So even if this was a 1, let's say 5 was the number. 5 means 101. When I divide 5 by 2, what happens? It becomes 2. It's like I cut off the last bit and I just keep the remaining bits. So this is 10. So that's what happens when I divide a number by 2. Integer division, right? So now that means my last bit is the first bit. First bit is 1, so I'll put a 1 here, and then I'll cut off this. Next, this becomes my last bit. So this is the second bit of the whole number. 0, cut off, 1, cut off, 0. How I find 0, 1 is by checking whether the existing b is divisible by 2 or not. If it's not divisible by 2, the last bit has to be 1. Odd numbers have their last bit as 1. So I think you'd be familiar with this finding the bits of a number, but I went through it once again. Now, so a power 2 power 0 is held here. If the last bit of b is 1, I will multiply a PWR. So a PWR is the a power 2 power I holder. So instead of 3, I put a here. So that will be a power. Now, when I go to the next bit, I should have a power 2 power I plus 1. How can I do that? I can square this number. A power 2 power I into a power 2 power I will be a power. So it's like a power x into a power x. That will be a power 2x. Here 2 into x is 2 into 2 power I. So it's 2 power I plus 1. In the previous case, I had stored it in an array. This time, instead of storing it in an array, every time when I find the ith bit, I am finding what the 3 power 2 power I is there. And when I go to the next bit, if I square it, it will become 3 power 2 power I plus 1. So instead of storing those in an array, without storing, I am saving space. I'm just using two variables, result, and the corresponding a power that I have to multiply. A power will hold a power 2 power I. If the last bit is 1, I'll multiply a power to the result, and then for next bit I have to square a power, and then I cut off that bit from b, and finally I return result. Right? So any doubts so far? I see no doubts. Any doubts? Okay, no doubts. So I'm assuming you understood how the fast multiplier works. But then, so the time complexity of the fast multiplier is log order of log b. We saw that in the explanation. Now, however, our computers can only handle integers only till 10 power 9. So if you want to give a number as an integer, the best case is unsigned long long, and unsigned long long gives you around 0 to 10 power 9 ish. But then, suppose you want to find 300 C100 itself, that itself is like a lot of digits. Or let's say it's 2 power 70. 2 power 70 has more than 20 digits, and our computers cannot calculate that. So if you don't know the number of, if you don't know 2 power 70, if in a CP question that is the answer, how would they test whether you've got the right answer or not? What they generally do is, they ask you to output that large number modulo some huge 9-digit number that you would have seen. I think in the contest also for one question we gave this number, 1E9 plus 7. So all this is another number that commonly comes, 998244353. Looks like some random pattern. No, I printed 9 twice, 4 twice, and 3 twice. So what's so special about these numbers? They are large, that's one thing, and they are prime, and they're also around 10 power 9. So these three factors are the reasons why these numbers come. So they are large because I'd want to have a large variety in what answer you give. I can't give the prime as print your answer modulo 2. That's like dumb, right? Because if your answer is 2 power 69, you will print 2 power 69 percentage to 0. Or if your answer is 2 power 70, that will also be 0. So they tend to choose large prime numbers like this. And why prime? Because only with primes you can compute modulo inverse using Fermat's little theorem. And 10 power 9 gives a big range, that's all. So now, can we modify a fast multiplier to output 2 power 10 power 9 modulo this number? So yes or no, you guys can put in chat. 1E9 plus 7 is the smallest 10-digit prime number. Coincidentally, 1E9 plus 9 is also a prime number, but sadly everyone forgets about it and asks only with this number. So yeah, can you, oh shit, spoiler, can you modify the previous code to output this modulo this, the remainder when this number is divided by this number. Note, there is a very useful tool that you have, AB mod n equal to A mod n times B mod n whole mod n. That tool you have to try to use here. So anyone has, can you multiply yes or no? Can someone put yes or no in the chat? That would be nice. Even if you think no, you can put no. Maybe there's another method. So okay, I think everyone has become tired or something. Yes, okay, there's one yes coming in the chat. So yeah, you can modify and you have to exploit this property to the most. Exploit property 3, which is AB mod n equal to A mod n times B mod n whole mod n. Now, how do I exploit it? Now, so this is the power function that we had talked about initially. So I'll define hash define mod and buzz. This is like, at least for the sake of this code, this is like writing const int mod equal to 189 plus 7, and then this is a general type def that I use. So what does the function do? It takes a and b as input and returns a power b percentage mod. My mod is this number. Note that mod need not be a prime here, even though 189 plus 7 is a prime. For this power function, mod need not be a prime. It need not be co-prime to b as well, right? Now, LL power LLALB. We will do the same thing. I will give a result and I will give a power. And interestingly, whenever I am computing, I am only multiplying more and more numbers to result. I am doing result equal to result into a power. So what I can do when I multiply something to result, I can ensure that the number being multiplied is less than mod. So what I will do, initially result is 1 and initially a power is a percentage mod. Suppose someone gives me a big number, I will take model is there itself, because AB mod n is A mod n times B mod n whole mod n. So there is no issue in converting A to a percentage mod. Again, we will go through the bits of B. If the ith bit is 1, result will be equal to result into a power, right? If the ith bit of B is 1, we multiply a power to result, and then we square a power. Now, initially a power would have been, let's say my a was 10 power 9. Initial result was 1, result will become 10 power 9 with this move, and a power will become 10 power 9 whole squared, which will be 10 power 18. Now 10 power 18 is more than mod. So what I will do, I will reduce a to something less than mod. I will take a power percentage equal to mod. Basically, I'm exploiting that property 3 to the maximum. If my answer consists only of products, whenever I multiply a number, I will multiply that number percentage mod instead of multiplying that number itself. So I will take mod here, I will take mod here, and I will go to the next bit of B, and then I will return result. My result, whenever I'm after multiplying, I'm taking percentage with respect to mod, so my result is ensured to be less than mod, and then I'm returning result. The time complexity is the same, O of log B. So we've kind of gone to a big jump from just knowing about what modulo is, just that small property of AB mod n equal to A mod n B mod n whole mod n. We have exploited it to find 2 power 10 power 9 when divided by this number, and we can't actually do it as an actual computation. We can't find 2 power 10 power 9 and we can't divide the number by this and find the remainder. But using this power function, using that property that AB mod n is A mod n B mod n whole mod n, we were able to find it, and in how much time? In O of log B time. So we were able to do it in 1 minute. In that computer where one multiplication took 1 second. Actual computers, multiplication takes like what? 10 power minus 8 seconds, let's say. So I can find this in 1 microsecond. In 1 microsecond, what I evaluated is 2 power 10 power 9. When I divide that huge number by mod, what is the remainder? So such a complex calculation with our efficient algorithm, you could say, we have been able to compute it this well. This is the power function. Any doubts? Can you show implementing this code? Yeah, I'll do that. Oh yeah, this is not bad. So actually what I have is I already have these functions stored in code blocks. So this is my version of the power function, highly compressed. So is it okay if I take till 3:30 or something? Can you guys stay back for 10 minutes extra? Is it okay? It's a nice topic as well, so I don't want you guys to miss out on the flow. So if you guys are okay with staying, please raise your hands. Or if Vineet is also okay with it, or else I can't continue. So okay, so cool. Yeah. So for example, let's say we do for some number that we know will be less than 10%. Let's say we fix A to be 2 and B to be, let's say 2 power 20. So if I do 2 power 20 percentage this thing, I should get 2 power 20 only because 2 power 20 is less than this number. So let's just check that once and see out power of 2, okay, A comma B, right? And no test cases. Okay, I'm not sure. So it gave some number 1048576. So let's check Google 2 power 20. 1048576. So we were correct. Now let's step it up a bit. Let's make it 2 power 200. And or no, let's maybe make it 2 power directly. Let's go to the higher step. 3 and 1e9, and I am finding 3 power 1e9 when divided by this number. What is the remainder? So let us see how much time it takes. Code blocks sometimes a bit slow on these. So 0.3 is okay. It's not even, that's for running and all, taking input and all. So such a big number, your code evaluated in such a small time. It just took like seconds. So I just pressed this and it came. That's all. So that fast was the computation that we did. Maybe I'll format so that you can see what's happening. So result is 1. Initially I'm taking modulus, and while B, if the ith bit is 1, I will multiply a. Basically this becomes the a power. This replaces the a power. This will store a power 2 power I percentage mod. So result will be multiplied that, and then I will square it, so it will become a power 2 power I plus 1. And then I take modulus, result modulus, I go to the next bit. So this feels like such a powerful tool. Instead of doing 1e9 iterations, we can even try that. For int I equal to 1, I less than equal to 1e9, and int r equal to brute forcing the product, and let's see how much time it takes. R into equal to 3, and by half, okay, and then we'll take modulus as well. R percent mod, and then C out R, right? That should work. Let's see what happens. Code running. I'm not sure if it will run fully. So it took 6 seconds to calculate this number. So if I put this in a for loop, let's say, this should not run. I am not sure what's going to happen. So it's going to compute, I think, 3 power 1e10 in this case. And code has stopped. So it should probably take 60 seconds based on the calculation. I'm not going to wait that much. Instead, what I'm going to do is I'm going to see out power of 3 comma 1e10. And that's it. I don't need to run any of this. Control shift. An answer came. So it is really important to appreciate that high efficiency that we're getting with the power function. Something that we can't, if we try to do manually itself, it didn't run at all. But then with the power function, it came so fast. So that's something that is true about all of the functions that we're going to see now. So yeah, I'll continue. Any doubts? You guys want me to illustrate something more? You can raise your hand or put in the chat. Anything's fine. Okay, cool. I'll go to the next one then. So now, function to compute mod inverse. Now that we have a very nice tool to compute a power b percentage p, we can use this to find mod inverse using Fermat theorem. So mod inverse is the b power p minus 2 percentage p. There will be power of b power p minus 2, and where the prime that I'm dividing with should be equal to p. So in the code for this, I'll just call power of a comma p minus 2. That's all. That's all the code is. Because I already have the power function. Time complexity will be log of the power. Here power is p minus 2. So order of log p. P minus 2p, not much of a difference. So that's mod inverse. So we were able to now compute mod inverse with a code and in 1 microsecond right now. If we had manually done writing for 9 and 4 itself took us a lot of time to do manually. So that's the power of computation and using this as an efficient algorithm. Now we're going to go into another thing. Computing n factorial percentage p efficiently. So how many digits do you guys think 300C100 has? Or at least give me some kind of lower bound. It has at least more than x digits. You can put some number that you think is the answer. So in the chat, so that I know you guys have not slept off. So okay, nothing has come in chat. Everyone has slept off, I guess. Or maybe everyone is busy computing how many digits are there. So if you're busy computing, do raise your hand so that I'll know you guys are computing or doing something. Okay, yeah, cool. Some have started raising. That's cool. So you can give me a very bad minimum lower limit. You can say it's more than 20 also. I'm fine with that. As long as you give me an answer that says more than 20, I'm fine with that. Because if it's more than 20, we can't compute with our computer. We can't compute n 300, 300 with our computer if it has more than 20 digits. So what I did was 300 factorial will be 300 factorial, 300, 300 is 300 factorial will be 100 factorial, 200 factorial. So I'll remove the first 200 numbers. And then I have 201 by 1 into 202 by 2 into 203 by 3, so on. And all of these pairs that I get will be more than 3, which means the answer that I'm going to get is going to be more than 3 per 100. And 3 per 100 has 48 digits. At least 25, at least 20. Yes, exactly. Definitely greater than 48 digits, because 3 per 100 has 40 that you can find using log. So this is something that I can't compute. And when you look at it, it looks so simple, right? 300, 300. It's like if out of 300 items, you have to choose 100 items. But then in code force questions, we are dealing with 10 per 5 items. So if we can't compute this itself, how will I, if I want to choose, if I want to do some choosing, how can I compute it? Again, we will go for finding modulo with respect to some number. Now, what do we do for finding n factorial percentage p? What we do is we pre-compute n factorial percentage p. So what we do, we compute this from 1 to 10 power 5 before running our test cases. This is a general strategy that we use because when we have like 10 power 5 test cases and all of them deal with 1000 factorial, I don't want to keep computing 1000 factorial every time. Instead, before running the test cases, just before starting to get input, I will compute from 1 factorial to 1000 factorial, and whatever factorial you ask me, I will have the answer readily stored in an array. So we do this kind of pre-computation for factorial. So and what idea do we use? We use the recursive idea. Factorial of n equal to factorial of n minus 1 times n. And memoization. What is memoization? When I find factorial of n minus 1, I will store it in some array. Next time when I want to find factorial of n, I will retrieve it from the array and multiply it with n. So given I know factorial of n minus 1, finding factorial of n is just one multiplication away from me. So this makes my computation process very efficient. Instead, if I have to find brute find factorial of 1 to n by just multiplying, so 1 plus 2 plus 3, that's like O of n square. Instead, I have a nicely efficient O of n code. So we will use small things like memoization. Memoization is like storing whenever you compute it, and this recursive idea to save both time and space. Space means memory space, not real life space. So how do we do that? I will declare an array. So let's generally we'll be asked for factor till 2 into 10 power 5 factorial, and I will declare an array and I'll make a function called make factorial. Factorial of 0 is 1, and then I will use the recursive idea. Factorial of I is I into factorial of I minus 1, and I'm storing percentage mod. This value is already less than 10 power 9. This value is obviously less than 10 power 9. So product of both will be less than 10 power 18. So I can store in my integer variable or in the long variable, and I'll take modulus to bring it to less than 10 power 9. And then once I've computed, I've basically declared the function and then I've called the function here, right? Time complexity is this for loop. The time complexity of this for loop is from 1 to fact length. So time complexity is O of fact length, depending on what they give in the question. So if in the question they say you might have to calculate numbers till 10 power 6, then so be it. Or if you have to compute only till 1000 factorial, you'll keep this as 1000. So yeah. Now, computing nCr percentage p. So initially we wanted to compute 300, 300. So now, how would we compute nCr percentage p? nCr is n factorial by n minus r factorial r factorial. So now, hence nCr modulo p will be, we will use our a by b idea, right? So we have a by b whole by c, n factorial by n minus r factorial whole by r factorial. So that will be, this is, we convert into a by b mod n is a mod n into mod inverse of b mod n. So n factorial, okay, this should be, I think, n factorial percentage p into mod inverse of n minus r factorial comma p into mod inverse of r factorial comma p. Some brackets and all slightly missed off. I hope you neglect that. This value has already been calculated, right? factorial of n factorial percentage p we have already calculated. Do you guys have any doubts in that? In that factorial of n factorial percentage, finding n factorial percentage p? Do you guys have any doubts in that? You can raise your hand. So n factorial percentage p into mod inverse of this value into mod inverse of this value, that whole product percentage p. So I have reduced this seemingly tough computation into just 3 steps. If I have written this mod function and I have done some pre-computations. Now, but we face an issue. We can't find n minus r factorial itself, because r factorial 1000 factorial is like what? It's going to have more than 1000 digits. So if I can't find, what do I do? For that we have a nice theorem. I'm going to skip on the proof now. I'll share the proof in the slide. If you have 2 numbers to give the same remainder with respect to p, then both of them will have the same mod inverses. So that is the theorem. So if n minus r factorial and some number alpha give the same remainder when divided by p, then and p is prime, this is a prerequisite, then mod inverse of a comma p will be equal to mod inverse of b comma p. So I'll send the proof to slides due to time constraints. So corollary is, if mod inverse of a comma p will be equal to mod inverse of a percentage p comma p. But then luckily I have computed r factorial percentage p using the previous idea. So as I have computed it, I can directly use it, and here I can directly use mod inverse of what I have computed. So n factorial percentage p into mod inverse of fac of n minus r comma p, because this I have computed in the factorial array, factorial here written as fac, and fac of r comma p mod inverse, fac of n minus r comma p mod inverse, and then fac of n comma p. We multiply all these 3 and we take whole percentage p, and we are done for nCr. Time complexity of this, it will be invoking this, assuming we've done pre-computations, it will be invoking mod inverse, so there will be log of mod. Log of basically the mod inverse will take time that is equal to the power. The power that will be here is p minus 2. So here prime is mod, so time complexity is of log mod. And similarly for nPr is even simpler. We have only one guy here. So fac of n comma p into mod inverse of fac of n minus r comma p percentage p, and time complexity is. Now what do you do in terms of coding? In terms of coding, all of these functions will be given to you. You just have to copy paste in code, and whenever you want to find npr percentage p, you can just call ll npr of lln comma llr. That's all, right? You don't actually need to know the logic behind all of this, but knowing the logic helps that you don't miss out on boundary cases, and it's also nice hardcore math learning, right? So yeah, I had planned on doing some questions, but I'll not do them now. I'll maybe put up a recorded lecture for them. And yeah, these 2 questions are simple. I'll send the links as well. I'll maybe send it now itself in the chat, so that you guys can try now. And any doubts so far? I think I probably took out on a lot of time, but I apologize for that. But this is a nice topic and I wanted to cover it in the flow. So any doubts that you guys have?
Aditya, I think you can cover one question.
Okay, I'll cover. Okay, cool.
Yeah.
So, okay, I'll cover bitwise tuples. So the question, currently there's no submission feature right now for this question. Question goes like, Chef has 2 numbers n and m. Help Chef to find the number of integer n tuples. So basically it's a group of n integers such that all of them lie in 0 to 2 pi m minus 1. Such that all of the numbers have m bits in their binary representation, and the bitwise AND of all the numbers is 0. How many of you are not familiar with bitwise AND? Can you raise your hand? So bitwise and not familiar. Okay. Okay, cool. No issues. So what bitwise AND is? Let's say you have a number A 1 1 0 1 1 0. Then I have a number B 0 1 1 0 0 1. The bitwise AND of A and B, A comma B is A and B. What it will do is, let's say this number equal to C. C will be, you check the ith bit of A and B. So first we check the 0th bit. If both of them are 1, I will write a 1 here, else I will write a 0. Both of them are 1? No. So I'll put a 0 for this bit. Both of them are 1? No. I'll put a 0 for this bit. Both of them are 1? No. I'll put a 0 for this bit. Both of them are 1? Yes. So I put a 1 for this bit. Both of them are 1? No. I put a 0 for this bit. This is A and B. So maybe you guys can try out an example. So A equal to 7 and B equal to 6. What is the bitwise AND of these two numbers? You can put in the chat. I think bitwise is not coming. Okay, no. So A's representation is going to be 1 1 1. B's representation is going to be 1 1 0. First bit 0, second bit 1, third bit 1. Now bitwise AND of multiple numbers is, suppose I have A, B, C equal to 1 0 1 0 1 1 0. Bitwise AND of A and B and C will be, if all of these bits is 1, that corresponding bit of the final answer will be 1. Even if one of them is 0, the whole total will be 0. Yeah, 6 is the answer. Yes. So yeah, for this 1 1 0, so 1 1 0 1 1 1 1 1 1. So bitwise AND of 7 and 6 is 6. For multiple numbers, if all of the bits are 1 only, this bit will be 1. Else it will be 0. Right? So you have to find number of tuples that you can form like this, such that all of them have exactly m bits, and the bitwise AND is 0. If the bit 0, what does that mean? Bitwise AND. Okay. Bitwise AND of n numbers is 0 means none of them. So maybe I'll take an example and show 1 1 0 0 0 1 0 1 1 0 1 1. Now the bitwise AND of these numbers is 0 because in this place there was a 0, in this place there was a 0, in this place there is a 0, in this place there is a 0. So even if one of the bit positions has a 0 in it, the bitwise AND at that the bit in the bitwise AND will be 0. Right? Similarly, there's bitwise OR, bitwise XOR. I encourage you guys to look at it. They'll help in coding problems. You get questions based on them. So now, can you find how many pairs, or if I have to reword it, can you find how many bit arrays are possible? So this is A1, A2, A3, so on. How many such combinations that you can form such that the bitwise AND of the resultant is 0? Basically, at each position, at least one of the numbers has a 0. Right? So maybe for now, don't think of m bits. Think of only one bit. Each number has only one bit. Basically, each number is a 0 or 1. So how many ordered tuples you can form? A1, A2, so on, such that each number is 0 or 1, and the bitwise AND of the numbers should be 0. So you don't just give me the expression. Let's say you have n numbers. Each of the numbers is either 0 or 1. The number of tuples you can form such that the bitwise AND of all the numbers is 0. How much is that? If you know the answer, you can put it in the chat after 2 minutes. Okay, fine. Someone has started, then you can start putting. Yeah. So I've got one answer. Is that correct? Do you guys think that's correct? 2 pi n minus 1. Or maybe could it be 2 pi n? Or can it be 2 power n minus 1? N into n plus 1. Okay, there's another answer. So I'll maybe mark the answers. And then n into n plus 1. And then I've got 2 power n by 2. Power n by 2. And 2 power n minus 1. One more. And okay, n into n plus 1 by 2. Okay. By the way, one more thing. If you have 0, 1, 0, 1, this is different from 1, 0, 1, 0. Two ordered tuples are these two ordered tuples are different, and 0, 0, 0, 1 is different from 1, 0, 0, 0. Right? So these two are different ordered tuples. These two are different ordered tuples, even though they have the same they have the same frequency of each number, because they're called ordered tuples. Order matters. Right? So I've got more votes for 2 pi n minus 1. So I've got one more thing. Okay, it's interesting. 3 into 2 power n. Remember the numbers a and each a can either take 0 or 1. Right? 3 into 2 pi n is one more answer that I've got. So we are now assuming each number can have only one bit, such that bitwise AND of all the numbers is 0. Any other answers? Or even if you want to vote for either one of these 4 answers, you can vote, right? So you can put in the chat. So now I've got a JEE multi-correct question. I have 4 options. Okay. So which is correct? Let's see. Any more answers? Is there a 5th option coming? Okay, I don't see a 5th option. Okay. Okay, Vatsal, can you tell me why you went with n into n plus 1 by 2? If possible, can you unmute? Yeah, Vatsal Arya has raised his hand. I think your mic features there. Yeah, cool. Are you speaking? I can't hear anything from your side. Can you guys hear anything?
No, I can't hear anything.
Okay, so okay, I guess then who else? Someone into 3 into 2 pi n, right? Oh, okay. So someone who into 2 pi n by 2, can you explain your logic?
Am I audible?
Okay, yeah, you have come. This is Vatsal, I guess.
No. Anshuman, 2 pi n by
Okay,
2.
yeah, 2 pi n by 2. Yeah, can you explain your logic?
Like I thought there are n numbers, so we'll divide into n by 2. I mean, we can group them into n by 2 groups.
Okay.
So each group will have either 0 or 1. So it can be either placed 0, 1 or 1, 0 in these ways. So there are two possible ways to place each the group. So I got 2 pi n by 2 like that.
Why does your group size need to be n by 2? You can have 1 and n minus 1, right? You have 1, 1 and all the rest are zeros. Still the bitwise and will be 0 because there is 1, 1 and all of them are zeros. Or you have all of them to be ones and one of them is 0. In this case, the bitwise and is going to be 0 because there is a 0. As long as there is a 0, bitwise and is going to be 0. So I think you've got the issue in your logic, right? Okay, yeah.
Yes.
So someone went to 3 into 2 pi n. 3 into 2 pi n. Okay, and I guess he or she is not there. So this is, so the answer is 2 pi n minus 1. Now, the only case out of all possible numbers that you can allot for each one, each a can mean 0 to 1. So each a has two possibilities. So you have 2 pi n possibilities in total. Now, the only possibility where the bitwise end of all numbers comes out to be 1 is all of them are 1s. Because we should not have zeros at all in our number. If we have zeros, bitwise end is 0. So the only case where bitwise end will become 1 is when all of them are 1. That is only one case. So in all other cases, bitwise end is going to be 0. Now, what do you think will happen if the number has m bits and I want bitwise end of the numbers to be 0? So for 1 bit, this is the answer. What do you think the answer is for n bits? Can you put in the chat? Yeah, okay, Gokulnath understood his mistake. Cool, that's nice. So if I had 1 bit, that is a good. Here in this question we have m. Each number has m bits, leading you. So number could be like this as well: 0, 0, 0, 1, 0, 0. So this also for now I'm considering it to be a number of m bits. So in this case, what do you think the answer will be? For 1 bit, we said that the answer is 2 pi n minus 1 because there's only one case where the bits could be 1. For this case, anyone has any answers? No answers? So if you want the bitwise end to be 0, all bits must be made 0. From this, can you do? Soham has given an answer. He's given 2 pi n minus 1 whole pi m. If the bitwise end of the all the bitwise end numbers should be 0, then all bits must be 0. From this, can you say something? You have to ensure that all of the m bits must be 0. 2 pi n minus 1 whole pi m. Another answer has come. Same thing. Any other answer there? Or is this the right answer? We still don't know this is the right answer. Any more answers? I guess that's it for now. So yeah, this is the answer. Reason is, if the bitwise end is 0, I need to ensure every single bit of the number is 0. And when I can form AI, when I can form a number of m bits, each bit I have a choice of what to do. So instead of dealing with the numbers, I will deal with the ith bit of AI first. So I will first take the ith bit of all numbers, a1, a2, so on till an. I will only fix the ith bit. Now, this bit must be 0. Bitwise end of this bit must be 0 because bitwise end of whole number is 0. Now, bitwise end of this bit must be 0 means I have 2 power n minus 1 choices for fixing this bit of the numbers. If I want to fix the next bit of the numbers, I will again have square. If I have 3 bits in my number, cube. If I have 4 bits in my number, power 4. If I have m bits in my number, power m. Now, in terms of implementation, the problem is actually very simple. So I have to get int n and m's on the user, and then first I'll form the bit 1 bit answer. Okay, maybe it's bit 1 I'll keep. Bit 1 equal to power of 2 comma n minus 1. And this value is always positive. Reason is power of 2 comma n is even, and even percentage odd can't give you 0, mod is 29%. So this is more than 1. So 1 minus 1 is minimum value is 0, which I'm fine with. This number is always going to be non-negative. And then maybe not int, I'll put ll, long int. And then ll answer equal to power of bit 1 comma bit 1 comma m, and that's all the answers. With the preliminary test cases, currently that question is not supporting submitting. So oh, I didn't get input. Oh no. Yep, it should work. You have to give an enter. Yep, so 1, 9, 25, and some big number. So generally when these big numbers match, your code is correct. So that's an illustration of how you use power. So once with the functions, your whole process became very simple. You just had to find the numbers, and once you found the numbers, you can just call the functions, and the functions will do their job. Right? So any doubts? So because this topic is a bit non-trivial, the questions also can be a bit on a difficult side. So try to solve the questions as much as you can, and if you can't, don't worry, there will be solutions uploaded so you can refer to them. Right? So that's all I have for now. Second question, I guess, is 3:15 right now, so maybe another day. Yeah. Any doubts? We'll share all the codes in the group, and I'll also share a short version of the slides so that if you want to read through, you can do that as well. So yeah, I guess that's it from me. It took a lot of time, so I guess.
Yeah,
I hope the session was good. Yeah.
Yeah, but even I hope people understood the part of how power works and real nCr works. So.
And one thing to note is every time you get the output from a power function, the number will always be less than 10 power 9 as well. You don't need to check it outside. So that also we'll take care in the function. So when we send the codes to a function, we'll send that way so that you don't have that issue as well. So yeah, over to me.
Thank you, Aditya, for such a nice explanation for power and nCr. I hope people understood that part. Once you have the code, like it doesn't matter if you understand the implementation for most of the problems, you can just copy paste the code and use it. So yeah, most of the times, if you get the logic, you can implement it using power. Like for this problem on CodeChef, if you got the logic that the answer is 2 minus 1 power m, then you don't need to think on how power works or how anything else works. You can just use that. We will share the code as well. So even if you didn't understand anything in this session, you can still use the code and can still work out all the problems. Yeah, we'll share the code so you can use it at that point of time. Okay, we are a bit late on time. Like we are a bit getting out of the time limit. I will just give a small introduction to STL and then we will end the session. Just give me a minute. Yeah. Can you see my screen, Aditya?
Yeah, I can see your screen.
Yeah, you can see, right? Okay. Also, my general template. Maybe I will erase it. Okay. So, basically, this is the STL library, right? And you guys have seen so far that whatever we are using is like coming out of it only. like all the things, all the functions you are using, or any kind of mathematical function or anything which you use, you are using that from this library. One of the most important thing which this library offers is the STL containers. I would like to give you a brief introduction to what the STL containers are. So I think till now, all of you have uh, used strings and all in some of the problems. So you would have seen that, okay, so basically uh, array and variables, and there is something some other thing also called pointer. So these are the tools that any language offers, like any kind of language, it will have these three things: a variable, array defined variable, and a pointer to a variable. So these are the basic things. After that, whatever you see is a different way of implementation in each of the languages using some libraries or some functions made by them. So these are the basics. But now if you see, string does not fit in either of three of them. So basically what string is, uh, there is a complicated implementation of string altogether, but to uh, to let you, like, as a you, like, this is kind of a mobile or a game kind of. A game is created on the back end, but as a user, you are only focused on using the input and output of the game. So you will play this, you will get this, and so on. Like, just like a string. So there is a complicated implementation of string that goes behind. But what we are concerned with is the user interface of the string, how we can use this. So now if we see, we defined a string S. Now we can just see in S, see out S. And maybe I will try it out. So maybe I will write. Yeah, I write KDVNeath. It took that as a string. It took it as an input, and it outputted it. Another thing which we can do it, and equal to s dot size. So now if you see, we have not done any calculation in this thing. What we are using is instead is a function that is allocated to us with the string. And that function, like that implementation that goes behind, is helping you to directly use it. So now I have used this, I will print it. Maybe I will write it again. So the answer should be 7, right? So KDVNeath, it stored it as a string, it output it as a string, and now it's telling the length of it. There are a lot of other functions with string. S dot. Just a minute. So like there are these functions of string compare, string copy, string assign. Maybe I will show you one of this. Dot. I will not input it now, and I will directly assign it. Let's say I assign it. Now I will use cout str. Not used to assign things like quite a lot, but yeah, let's see if it works. Okay, so it's giving output VF 5 times. Okay. Yeah, so it's assigning A 5 times. It's a simple thing, but it's making your implementation quite easier, as you can see. Like else, what you would have done is you would initialize a for loop and you will assign 5 times. Instead, you can just put this line and it's done. You can also check its length again. A dot size. And we can see after that. Yeah, so there are 5 ways followed by the length, which is 5. So as you can see, it's a simple thing. It does not take a lot of implementation, but what actually you are using is a complicated implementation is done behind, and now you're simply using its output. So this is string, and which, like, the things are pretty simple. Even here, what it's helping is to get things done pretty clearly on the user interface. So here, instead of initializing a for loop, you can just use this term which is assign and The name is also defined in the same way, which will assign 5 ways to the string. So that is something which eases your implementation at the user end. And similarly, we have a lot of other containers. This is just one thing string. Similarly, we have a lot of other containers for which implementation is even not trivial. But again, as you see it in the power and the modulo thing, once we have the implementation done properly and you know what its limitations are, what we actually does matters is how to use it, right? So once you know the power implementation and nCr implementation, you can just maybe copy paste the code and directly use it. So similarly, there are a few things that are inbuilt in this library. So for that, you don't even need to write a code. You can directly use it. So maybe I will tell you one of the things. So just as an array, what you have seen is right, like we need to initialize the size of the array and then give input one by one. We have another thing called vector in which you don't need to allocate the space, like allocate the space initially. You can just allocate the space as and when you get elements. So suppose I will add 10 elements. I will add 5 elements maybe. And now after that, I just want to print all the elements. So I will use another function which is inbuilt in this library, and I can just use it as a user face. So, yeah. Yeah, I will just come to that. Yeah. So as you can see, I have not allocated any space to this. Still, okay, I need to take it as an input. Yeah. As you can see now, these are all the functions that are associated with this container vector. This is add, back, begin, capacity, constant, clear, empty, flip, pointer, max size, pop, reserve. What we are going to use for now is pushback. And what this does is this will push the element you give into the vector. And now in the end, I will just output all the elements. Let me just try it out. Yeah. I will give 1, 2, 3, 4, 5. So yeah, it outputted all the 5 elements. So this is just a simple thing which is associated with vectors. There are a lot of other functions as well which this offers. The important thing is once you know how to use it, you don't have to worry about how it's implemented on the back end. But what our focus will be on the next week is to learn these kind of special containers which offer a lot of special properties with them that will make your implementation clear, and sometimes it will help you do things which you would have not been able to do otherwise. So these are the things, vectors and other things. These are some things which look a bit complicated when you see it first of all. Like even now when you would be seeing it, I'm not sure how it goes to you, but maybe when I first saw vectors and all, it was a bit confusing to me. I thought, okay, what is this? Till now I was using only arrays and all. What is this? What is pushback and all? So I was a bit resistive to changes, like I wouldn't adapt to them very quickly. I would try to neglect them until I can. But I would really advise you not to fear of these things. These things would get simplified over time. As and on when you will use them, it will become very clear. So just focus on understanding them and just try to use them over time. Just don't fear from them and don't use it. So try to use them, try to get familiar. Only then you will be able to use them very easily. And once you get to use them very easily, a lot of places and a lot of times where your code could have got very big and very complicated, you'll be able to simplify it much, much, much better. So I hope I could have been able to give you guys some idea of what HTML containers are and like what are we going to learn in the next week. This will be basically a lot of HTML containers which would offer you a lot of special properties to use them in your code to simplify and to do things which you would have not been able to do otherwise. Does anyone have a queries in the small part of vectors what I have done till now? Don't worry about the implementation. Implementation is something which will never be worried about. It's just about the usage. So once you know how to use, you are done with it. You just need to know the usage, how you use the code. Yeah. Does anyone have any queries in this part of how we use vectors and what strings are actually and what we will be learning the next week, the most importantly. So I just wanted to give you guys some insight on what we will be learning. Because STL is like literally as said, the most important functionality which this standard library offers. And you will yourself be able to appreciate the amazing things which you can do with the STL containers. You don't need to worry about what goes on behind. You can just kind of have the user experience and use it as you need. Yeah, even still, you will get a lot of problems using, even after using them, it would be like you would have to think on the logic part, but you can now take the interface or the code that is written for granted. You don't need to worry about that. These are implemented with so many people and so many like professionals that these are quite perfect. So yeah, does anyone have any queries in vectors or string part, whatever I did till now? Okay. Okay, guys, if there are no more queries, I think it's already over the time. So we will end the session now. I hope you guys got some insight on the power modulo and sieve of electrolysis and also what we'll be going for the next week. We will have the contest this Sunday on 4 p.m. And again, it would be the same thing. We will have 10 problems and you would have 2 hours to solve them. And we will announce the winners on the Code Forces blog. Okay, guys, then see you on this Sunday. All the best and prepare the best you can. Bye-bye.
Yeah, thanks a lot, guys, for staying till now. All the best for the third contest.
Saptashi, you can end the meet, I guess.